Recording is on.
Okay, we are good to go now.
Okay. Let's get the show on the road.
Yep.
Good evening, everybody. Welcome to the October 19th meeting. Nobody's new here. Oh, Bob's here too. Yeah.
Don't forget
So-
to mute the mics.
What's that?
Just saying, reminder, mute the mic. I'm hearing some background noise from somewhere.
Yeah. If you guys, if you're
Yep.
not speaking, mute your mic, please. So anyways, so tonight, we have Peter. He's going to talk about designing a front end amplifier. And then after that, it's pretty much open. So we can do a round table. Next month's mid-month meeting, I'm going to do a presentation on toroids, which I've done like 3 times, I think, already over the years. So I'm going to basically do the same thing, but I'm going to expand it on some real life situations. And I think we're ready to rock. So go ahead, Peter.
Okay.
Recording is on.
Can we see that?
They've started a recording. Yeah.
We can see that?
Yes.
Okay. So designing a front end amplifier. I call it the V3OOI and the V3POA way anyway, but just because I wanted to go down with Dave at the same time. But no math in this one. It's just basically a little bit of an overview of what we've started off to do. And while I throw Dave in this equation as well, it is kind of the way I look at things, and then Dave and I have a good discussion about it after the fact. So I start off with, basically, what components am I going to use, discrete or IC? Usually it's a combination of both, but I prefer to use ICs where I can. I know like Bill likes to use discrete and everything, but if I can use a chip, I certainly will. SMD or through hole, I much prefer SMD. If I have to, I'll use a through hole, but for the most part, I'm pretty much all SMD. Having said that, the crystal characterizing board working on today, that's through hole components. So that's what we're working on there at the moment. I have one, and I went to look for it, and I can't find it. And I know I saw it about a month ago, and now that I'm getting ready to do some macking crystals, I can't find the thing, so I have to build a new one. Okay, and of course the other thing is the paper trail, or is the paperwork. Do a lot of reading and all that kind of stuff, which I seem to always forget to do. I'm always in a bit of a rush, but I am getting better at it, and that's of course to determine what the previous and next stage requirements are, and then go from there. Research the usual stuff, data sheets, internet, books, all that kind of good stuff. My library got built by Christmas wishes for about 3 years until the family started to revolt, saying they didn't want to buy me any more books. In the bottom graph down there, picture down here, this circuit here, this filter circuit, we use this one in the SNA. And this circuit over here actually is identical virtually to the 1253 that we're working, and Dave and I are working on at the moment. In this case here, they're using the AD8008, but it's a direct drop-in with the LT1253. I kind of go through, once I choose a circuit, I'll go into, is it my own design? And if it is, then I go right to LT Spice. And then I go over to a breadboard or a PCB. I very rarely use a breadboard anymore. I found measurements are so inconsistent and flaky and all kinds of stuff that I generally go right straight to a PCB, and then of course could go back to Spice depending on the results. If it's somebody else's design, then I'll go straight to a PCB. Now I show KiCad work after all that, but sometimes the KiCad work goes above that. the PCB stage for obvious reasons. And then of late, thanks to Dave and his efforts with JLC PCB, it's now coming to a point, especially if your board is 100, it's small, no larger than 100 by 100 millimeters. Etching and milling your own board now is starting to become not so cost effective. Now, for the first generation board, I'll do here in the shack. But after that, and this is what Dave has done, he's designed our first point of proof of concept boards and sent them out to be done by JLC PCB, and we're getting 5 boards for $7. So when you break that down to cost per board, I can't even buy the PCB material by itself, let alone etch it or mill it for that kind of money. So, like I say, if you can, maybe Dave mentioned in passing, I don't know later, but I'm not sure how long their delivery is, but I think it's about 3 weeks, I think, isn't it, Dave, or 4 weeks, maybe at most 3 weeks.
Yeah, I think it's 2 weeks. I'm averaging
2 weeks. So I mean, that's not a bad turnaround. Anyway,
and it's $4 US.
What is? Oh, $4 US. Okay. I'm wondering what a board, Dave, would cost that's larger than 100 by 100. Say another 50 mils each or something.
Yeah, I'm not sure. There's not a calculator where you could plug in the dimensions and it'll spit out the price. Either way, like I say, keep it at 100 and 100, and that's a pretty good prototyping board. It can prototype all year like that. So just to do a quickie here with the LT1253 chip, one thing that's nice is the LT Spice has a simulation circuit in there, and you can see it's set up there with the transmission line and 75 ohm impedances due to the video amp stuff. Dave did an LT Spice for the LT1253, and that's the circuit there that I put on. We've been testing of the last couple of weeks, and thanks to Dave's presentation last month and another simulation I have for the Stockton Bridge, I put this kind of stuff over here. I won't go into any detail on this one. Maybe another meeting I might. But here's what Dave talked about last month about making measurements, which you'll find these in the Spice Air log. And excuse me. And up here, I'm just setting up some parameters for the voltage and frequencies. And in here is the T delay, P span, and T span. Those are numbers there to basically center and display how many cycles you want to see on your plot. So the LT1253, it's a low cost, depending on how cheap of a ham you are, that is. Dual current feedback amplifier for video applications. So if it can do video, it should be able to handle our 1 to 30 megahertz range without any effort. It's ideal for driving low impedance loads, which is great because we're working with 50 ohms and wideband and high slew rates. Excellent linearity, and they claim flat to 30 megahertz, 0.1 dB. I didn't quite get that good, but not bad. Of course, my setup is nowhere near like theirs, I'm sure. The upper left is just a simplified view of the LT1253. It's got, like, I don't know, a dozen transistors in the thing, and then down the bottom is just their application for the video amplifier. That's just lifted right out of the data sheet. And we're looking at the LT1253 one because we were looking what's out there for the best possible RF amplifier for the best cost. We also were quite interested in low noise, and that was one of the things that led us down a rabbit hole that I eventually stopped going down, even though Dave and I just had another friendly discussion about noise. But I'm not too sure how we're ever going to resolve that one, if ever, and I'm not too worried about it. If I can see the signal, then that's good enough. And the other good thing about the 1253 is that the model for it is native to LT Spice, so you don't have to go looking for somebody else's take on it. And the pictures are just examples of some projects I found that they're using the LT1253 to something similar that we are doing. There's one. Here's the other one, and this is the other one down there. So the next thing I did was to get started for characterizing the 1253 was to set up a test board for it. And what I decided to do was I thought I had an SMD version of the 1253 on hand along with the dip switch. So I decided to go with a breakout board. So I designed the breakout board, which is over here, and pins 1 through 8 are matching pins 1 through 8 on the chip itself. So that should help me with my confusion when I start putting things upside down and all that kind of good stuff, which I actually thought I had to do once. And it just plugs into a pin header that's on the board. And when I was ready to do the SMD version, just plug it in and away I go. I wouldn't have to redo all this other circuit stuff. And the other advantage too is the AD8008, which I do have on hand as well. It's pin for pin compatible, so I can plug that in if I decide to take a notion to do so, and see how that chip compares to the 1253. But I think the 1253 works well enough. The board on the right is the layout for it. That's the first version board. I did end up doing another version because I don't know why I did this, but I put a pin header on here for an RF out. And again, when you're measuring, now I'm trying to measure signals like 110, 120, minus 120 dB and stuff like that. And all you have to do is just breathe on something and it starts, skewing the results. So I did another version board and put an SMA connector instead of the pin header, and that rearranged things a little bit. The other problem I had was this pin header was on the top of the board as well, and the pot for the second stage of the op amp was here, and fortunately I had a trimmer that had the adjustment on the side, because after I finished everything, I realized that the breakout board would now sit right over top like that. So that made it a little bit awkward. So the second version has the pin header underneath, so that I have easy access to the adjustments. So after I get all that work done with the KiCad and happy with that, I then develop the Gerbers, and I import the Gerber files into a program called FlatCam. And okay, I got version 1 identified up there, but this is actually the version 2 board, and you can tell that by, like I say, with this is the output here, the SMA connector up there. And in FlatCam, what you do is you are telling the program what kind of milling bit you're using, what depth you want to go into the board, the number of passes you want to make around the traces, and the percentage of overlap on the traces. You can do other things in FlatCam. You can add pads, maneuver things around, and all. I think some graphics you can put in it, but I've not gone down that path yet. I still haven't spent the time to figure out how to use the drill holes and also the cutouts, because in FlatCam you can set up so that your milling machine will drill all the holes for you, and will also route out the board. And so you save you from using a hacksaw with it, but I haven't spent the time to do that yet. So after you do that, the FlatCam will generate the G code, and then you import the G code, and I use a program called Candle. And this particular board, it'll open up like this. This over here is kind of representing the milling bit. When you're ready to go, it does change into a graphic that rotates around as the bit, and you can see the path that the milling bit is going to be taking. That's what all those dash lines are there for. But the other thing you do with this is you set up what's called a mapping routine, and in this case here it'll be a 5x5 grid pattern, and the milling bit will come down, touch the board, and measure the height in this 5x5 grid pattern, and that seems to do a pretty good job. So you don't get some parts of your board maybe not breaking through, or some parts of the board where you're gouging in It does spit out the different height levels, so you can tell, how much your board is wavering. So, and it does move around a lot. It's not move around, but it does vary around a fair bit. So there's the board there. Over in the bottom right, you can see the stack of attenuators I have. I wanted to get down to, like I said, I think the lowest I went was minus 123. I think I'm in Dayton this year. I think I'm going to look and see if I can get a 50 dB attenuator or something like that. Maybe lower the stack down a bit, because it's not the first time I've had to put a stack of attenuators together. There was one project I did there. I think I had about 10 of them all on there. And on the left is just a closer up view of what I was talking about, where the breakout board for the 1253 is over top of the pot that's sitting underneath here. And there's the other pot over there for the adjustment for the first stage. And there's, like I say, I was using pin headers there for the RF out, which, as you can see, is not probably a very good idea. So Dave, make sure Ken, make sure Dave's mic is muted at all times, please. And I don't want to get into another conversation. It's noise floor. I never changed it. I know it's not noise floor. The noise figure, I know all that stuff is all opened up. Well, it's actually not opened up for debate. We know it's not. That's not what it is. But for the sake of it here, if I say noise floor, I don't really mean it. Anyway, this particular one screenshot is when I did 120 minus 120 dBm input at 14 megahertz. And the output I was reading on that from the LT1253 was 105 dBm. So the bottom line there is, you can see it when I'm getting down that low. So about 120 minus 120 dBm. That's about S1, I think. Here I did a sweep from 1 to 30 megahertz. The range I got was 1.36 dB. So Linear is saying they got, what was it, 0.5? But I don't believe them. But anyway, it's still pretty good. And that was the input I used there at minus 111. So that's just under an S3 signal. Here I went to a 123, and it was about 7.4 dB above whatever that big long line is along the bottom. But the bottom line is, you can see it, and if you can see it, then we should be able to hear it. Just decided to throw in the first version. This actually might be the second board that Dave and I did for the D612 project. 1253 lives up here. There's the 612 for going into the mix to the IF there. Some extra wires in here. I thought was a good idea was hooking up looking at the bandpass filter, or sorry, the crystal filter. I just wound a few turns around the toroid and fed that into the spectrum analyzer instead of tapping off and things like that. I know Dave did it differently, but I thought that was had less effect on the circuit. Whether that's true or not, I don't know. And here's the board that Dave designed for the receiver for the Phoenix 612 project. And there's the QRP Labs filter. Basic stuff, the routine. There's the chip that goes in there, and then we still have the pots in there for adjusting the 2 stages. Possibly we might, I don't know, maybe going down the road, maybe this pot will be fixed and this one will be will stay as a pot, so you can do some adjusting for the RF gain circuit. But anyway, I find that adjusting both, giving a little bit of gain, having gain on both of them is a worthwhile thing instead of having one shut down. That's about it for that board, I think. Oh, any questions?
Yes, I have one.
Yeah, go ahead. I can't see who's putting their hand up there.
Oh, that
Ken,
was
Ken.
Ken, I'll let you do that, Ken.
Yep.
Okay. Yeah, go ahead, Kevin.
Like you said, the output was rated at like flat to 0.1 dB,
Is that what I
and you were getting like 1.3 or whatever, 1.4.
something like that?
Yeah. So I'm just curious, like, does KiCad not have like a function? Like, well, first, I guess the first question is, do you think that's related to the layout of the board? And if it is, does it not have functions where you can do like strip lines and do like 75 ohm traces or 50 ohm or whatever? I'm just curious. I wonder if that has any effect, because you're getting some pretty good performance here, right?
Yes, I think so. I don't know exactly. You know what? I should probably go back and take a look and just see what they did for. I mean, they show an application circuit, but I don't know if they show some data sheets have the circuit out that they use for testing.
I'd be curious if you took the chip out of the board,
yeah,
and put your SA on it and see what the nominal impedance is of the input circuit and the output circuit, and how that varies, and does it change with, like, is it related to your 1.3 dB variations that you're measuring?
Don't know. I think further exploring, I guess.
I'm trying to give you another rabbit hole here.
Yeah, I'm afraid to go down it. But no, it's these are kind of questions. These questions you have here are some of it already thought of, and how do you go about it? As far as KiCad with that other stuff, maybe Wayne might know, but I'm not sure about the strip line stuff that's in there. If it is, I haven't gone that far down that rabbit hole.
Yeah. Anyway, I just wondered, because that's a fair bit of, that's a fairly significant difference from the chip spec.
Well,
that's why.
There's two things. I was reading an article that talked about this very thing, and one of the things they put out there was they'd run all these kinds of tests. They take the best case scenario, even though it's an unrealistic setup that they've probably done is pristine, and not only that, the marketing people get involved. So between what the engineers have done, and then the marketing people take it to another step later, and that's the results that you see. So it's rare that you can really match what you get. But I will say, while I was happy with the results, I was a little bit disappointed that I wasn't closer.
Well, yeah, it's kind of like writing an app in a weekend, right? You only want the good part of the story to get out.
Yeah.
Right? So,
yeah.
All right, go ahead,
anyway.
Dave. Go ahead, Dave.
I got to take myself off mute. Peter, a couple questions, if I can remember now. Yeah, I think 1 dB variation is nothing.
I agree.
Because given your experimental setup, Kevin's right, the board, you're milling it, the traces are not ideal. Like if, linear or whatever they're called now, analog devices, when they go and they do these tests, their test boards are all got proper grounding, and they got all these vias tying the grounds together, and they've got strip lines, and they do everything in a very professional way. And so that's great, but for you and I, 1 dB variation is fine.
Oh no,
I think, Peter, it's pretty impressive that you got 1 dB.
I mean, look at it this way, Dave. On my board, as you saw there, I have a pin header there, and then a pin header sitting on top of a breakout board that's sitting on, and on top of that is an IC socket, and then the IC fits in that. And they're probably using an SMD chip that's soldered right directly to the board. So there's a lot of. And
well,
plus,
I think I'm surprised you got just 1 dB. I would expect to get a lot higher, but that's pretty damn good, I think. Next question is your footprint you got for that SMA connector. Where did you did you have to make that yourself, or is that standard in your CAD?
That I found it somewhere, and I found it when I was using version 5 point whatever at KiCad, and I was using that for the longest time. Today, and I have not used the version 6 yet, and I decided a few days ago to actually start using it, so I had it all loaded, ready to go. And today,
when I had to redesign the crystal board, I started to use it in KiCad 6. And when I opened up the old file, I ran into all kinds of problems. So long story short, I had to go searching for another SMA connector because I couldn't find the SMA connector, or something broke on the version 5 thing there. So I did find another SMA connector footprint. It's not the same as that, but I think it's actually better than the one that you're seeing. But I can send you a
Yeah,
link.
because let me just hang on a second. Let me just see if I could get this. Yeah, so I just ordered this. Let me just share my screen here. I just ordered this last night. Let me see. How do I share my screen here? Sharing. There it is.
No, it's not.
Can you guys see this?
We see everybody as you see it. No.
Can you see this?
Yeah.
The Amazon?
Yeah, it's there. Yeah, it's there.
There you
Yeah.
go.
So I just bought these. These are IPEX connectors, and you can get pigtails for them. So I just ordered a bunch of those from Amazon last night, and I ordered a bunch of pigtails here. And what this is, it's got a IPEX connector at one end and an SMA at the other end. And the IPEX connector, I was just showing you, it's the SMA, it solders on the board. It's a well-known footprint, and it's really low profile. And I figured this is pretty good because it's low loss. And typically this is used for a lot of Wi-Fi and GPS type stuff. So it's good at high frequency. So I figured it's got to be good here, right? And for, $16, you get 5 of them. I thought that wasn't too bad, right? So that's what I'm going to start using now as a connector.
So
Yeah, the GPS modules do use that connector. They all do.
that's a pretty small connector.
It is, and it just your thing snaps into it, right? And worst comes to worst, you break it, you just unsolder it, put another one on. They're cheap enough that you could just replace it easily. The SMA connector, like you're doing a surface mount, and if that breaks, it's going to take the pad and all the stuff with it when it breaks.
I usually break a trace somewhere else in the circuit. I've yet to break the SMA part, but anyway, yeah.
So if I was going to do that, I'd get the through-hole version of those SMA connectors. That way, you've got some mechanical strength because it's mounted directly to the board, and it's going to be a lot harder to break that trace.
Well, that's what mine are. They're a slide on. They're an edge connector, so they go in like that.
I use the same.
Yeah.
I use the edge connectors too. Yeah, I use those.
Yeah. Any other questions?
Did you have to do any matching for that amplifier?
Just what was designed. The circuit is designed for a 50 in and 50 out.
Oh, okay. So when you go to the 612 or whatever, or no, you're going to the crystal filter.
Well, we'll be going to going to a crystal filter. Yeah.
Yeah,
I mean, there will be some matching. Yeah, there will be some matching going on there. Yes, of course.
Yeah. Okay.
Well, transformer matching.
Yeah.
Yeah. The other thing, Peter, I noticed on your board, you had along the bottom, you had a long trace that was running power to the to do the half voltage thing for the op amp, right? And the general rule is anytime you've got a long power trace, at the end of the power trace, you got to put a decoupling cap. You got to put a 0.1 microfarad or 100 nanofarad there because that trace picks up RF, it picks up noise, right? So that's one of the things I do a lot in the boards I'm doing now is anytime I've got a long power trace at the end, I put a decoupling cap.
So define long trace. Like more than 4 or 5 inches? 4 inches? Did I lose somebody?
I'm,
Oh, you're muted, Dave. You're muted.
yeah. Did you hear what I said about the traces? Any
I heard what you said about the long trace. I was just saying, what do you call a long trace? Something that's 3 or 4 inches long?
yeah, any trace that's a couple of inches long, I put a decoupling cap there, just because that trace could pick up junk or could pick up noise.
Gee, wouldn't that be great if I put a cap on there and I got 0.1 dB?
Yeah, there is a yeah, I don't think so. There's a video I came across where there's a formula the guy has, and he says that if it's this frequency and the dielectric constant and blah 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 blah, and he works out what the per frequency, what the minimum length is that you'll need a decoupling cap on. So I don't bother using a formula. I just say anything that's an inch or two long, I put a cap.
And it doesn't hurt.
Caps are cheap.
It doesn't hurt.
Yeah, it doesn't hurt.
Good thing I bought 100 of those 0.1 or 100 nanofarad caps, eh?
Okay, anybody else? No, I guess not. All right, very good, Pete. Thank you. That was interesting. So, does anybody have anything in particular you want to talk about or discuss or anything along that lines?
I have a question.
Yeah, go ahead.
It's Michael. About KiCad. I tried to download it, and I'm not sure what happened, but it ended up, I think it downloaded okay, but then when I tried to install it, it said it was going to take 9 hours. So I don't know whether I've done something wrong. But surely it doesn't take that long to download the program. It just would take just a few minutes, you would think.
Download or install?
Well, to install, yeah, to install it once it's downloaded. Or does it take a long time, or was I like
Turn off
sure it
turn off your virus scanner.
Hey?
Oh,
Yeah, okay.
I can't recall. I just downloaded 6 there the other day on the other computer here, and I'm sure it only took less than 5 minutes.
Oh, okay. All right. That's what I wanted to know. I'll have to try it. And I haven't used it, so I guess I'll try it out and see. Okay. Thanks.
Windows. Go ahead, Kevin.
Okay, hang on, just coming back. Just something I ran across, I don't know, whatever, last week or something. But I don't know if anybody's heard of the Internet Archive. It archives a lot of like web pages and stuff on the internet, and you can go back and visit old versions of web pages and old documents or whatever. But they're looking for donations from ham radio operators, and I'm just going to put the link in the chat that talks about this. They're looking for anybody that has like old ham radio stuff, information, I think like magazines, stuff like that. They're trying to digitize all this stuff and put it as part of like some archive type selection. So I thought, if anybody's interested, they're looking for books, magazines, documents, catalogs, manuals, videos, personal archives, no matter how big or small, podcasts, newsletters, all this kind of stuff. And they're putting it in a digital library online.
Is that the Wayback Machine?
Yeah, that's the same. Yeah, it's the same organization. Yeah.
Yeah.
So if anybody's interested, there's a link there in the chat. You can go check it out. Just thought I'd mention that. It sounded kind of cool. So anyway, that's it.
Does anybody else have something up?
Yeah, I got a question. Or not a question, but just curious. Last week I was discussing
with a couple of local guys here at our breakfast on Saturday about doing circuit boards with the JCLP CB, and the chap I was talking to came up with he asked me if I'd ever done a multi-layered board, and he was mentioning that this company JCLP CB, even with a 4-layer board, it's not all that expensive either. And that kind of opened, and I've barely given a thought to a double-sided board, let alone start thinking about a 4-layered board. But having said that, and with these prices so cheap, maybe that's in the cards somewhere down the road. Not 100% sure what you'd put in those layers yet, but it was an interesting thought anyway.
Wonder
Yeah,
how they make those things.
Pardon?
You'd run signals.
Go ahead, Dave.
Sorry, what'd you say, Dave?
I said typically in between the top and bottom layers, that's where you're going to run planes, ground plane, power plane, stuff like that. And in the middle, you run your signals, because your signals like to have a ground plane or they like to run over or above a plane, right?
So I was sort of thinking that you'd have your signals on the top level, and then you'd have your second layer could actually even take care of any jumpers that you would need. Or you could put power, I suppose, on the middle layer too, right?
Yeah.
Yeah. You're not. I don't think you're supposed to run power in a middle layer. You're supposed to run it, and I think the top or bottom layer. I'm not sure, but there's a whole science behind using multi-layer boards, and for us, why would we want to go to 4-layer board? Because I think most stuff we could do, we could get across with a 2-layer board, even a single-layer board, right?
Yeah, we've been getting pretty good with single layers, but I tell you, it's getting to the point where you really need the double, a 2-layer board. But like I say, take a look at the price of a 4-layer board on that website. And then that might get you thinking a little bit. Were you asking a question there, Ken? I didn't hear it.
Yeah, I'm wondering, how do they make those boards? Do they
glue them together?
They do
make 2 boards, and then they sandwich them together.
Oh, okay. Cool.
That's why you don't put components in the middle layers.
Won't be able to glue them together. And I take it the through holes go through everything then.
Well, you know what? Actually, having said that, I was reading something. I can't remember exactly what the article was about, but it talked about, and I started to do this when I started to mill boards. I was running thicker traces wherever I can, and then when I come up to an SMD pad, especially the smaller ones, I then narrow down the trace just before the pad. And then this article I was reading was talking about I'm creating an impedance mismatch kind of thing there. I thought, oh boy, here's another rabbit hole that I don't want to go down.
Well,
Sorry, Kevin, go ahead.
Oh, no, I was just going to say that, talking about impedance traces and strip lines and stuff, 4-layer board lets you do that a lot easier because you've got a ground plane to work against, right? So by setting the trace width and the, whatever thickness the board is, then it's a lot easier to do like your constant impedance traces.
In that case, yes, but when you're milling in the shack and you're getting down to some pretty fine
right,
stuff,
yeah,
you're taxing the ability of the mill. How do you get away with it? Well, go down to that really small stuff for that little last 1/4 of an inch or something. Anyway.
Yeah,
I mean, the frequencies I'm dealing with, I don't think I have to worry about it, but nonetheless, it was an interesting article. Maybe I read too much, not enough doing.
Yeah, Peter, there's a really good video I came across, because in light of what I'm doing with this board and all the coupling, I'm getting all the parasitics. So I started to look at PCB design, and there's a video the guy's got. He's got the 5 most common mistakes someone makes when they make a PCB, and trace width was one of them. He said using the wrong trace width, because he said it's kind of interesting. He said if you use too thick of a trace and you're running a frequency across it, you'll get more pickup or you'll get more radiation. So he said typically with power traces, you keep those thicker, but with signal traces, you use those thinner, right? Ignoring impedances and ignoring strip lines and that kind of stuff. Because he was saying using a thinner trace, you pick up less parasitics.
Did he say what size? Did he recommend trace sizes?
Yeah, he does. He goes on to there's calculators you can get as well. He was showing all kinds of online calculators you can get, like what Kevin's saying, where if you want to get the right impedance for the trace, you put in the parameters, the ground plane below it or above it, the dielectric constant, the width of the trace, the thickness of the copper too. You put all that stuff in the calculator and it spits it out. And I believe KiCad has that calculator in it. If you go into tools, you'll see it's got calculators there. Because I've used some of them. I used the one for power current versus trace width to make sure your trace width is going to be able. This balancing robot I did, because I have to use high current. So I wanted to make sure the traces, because that board, if you look at the board, it's a board I made from JLPCB. So I had to make sure the traces I had could carry the current, right? So I used that calculator to find out what my optimum thickness of my trace width had to be.
For the signal and trace with that kind of thing, are we probably talking more VHF, UHF, and gigahertz, all that kind of stuff than we are at HF? I would think.
For us, Peter, I don't think it matters. I think there's some general things we could do in terms of traces, but I think, like the board I made, I was so careful to try not put components close together to get coupling, and I still got coupling coming across. But as I said, I don't know if someone could comment on this. I'm getting coupling, but it's of the order of about 40 dB down. So I don't know if that seems okay. Like 40 dB bleed through seems like pretty low. I don't know if someone could comment to say that's correct or it needs to be lower. I'm not sure.
When you think about it, Dave, a few years ago we wouldn't have been able to measure that, so we would have never known it was there. So hence the question, like I say, or is this abnormal? There's something wrong. And this is just the first time we've noticed this, or you've noticed this.
See, this is a side effect of buying expensive spectrum analyzers. Don't buy the spectrum analyzer and you're happy.
Why don't you buy one yourself and you can join the pain that Dave and I go through?
See, I have less hair. I have less hair now.
I guess the bottom line, Dave, is what do you see on the end? Is it interfering with anything as it goes further up the chain or down the chain?
Yeah, see, I'm just tracing it through and I'm seeing 40 dB down. And 40 dB, I think that's a lot, because if you look at what the spec for Industry Canada for harmonics, it's 44 dB down. So 40 dB down on your traces, I think is perfectly acceptable.
And what was the fundamental power?
Oh, I don't know. That was the difference. It's like minus 70 something. I don't know. Where did I put the numbers?
minus 40 dB from the fundamental of minus 73. So
minus. Well, it was minus 10.
Oh,
minus 10 dB signal coming in, right? And I'm seeing like of the order of minus 70, but I've got a 10 dB attenuator on the SA. So, you know, minus 10, minus 70, you take away 20, comes down to about minus 50, minus 40-ish, minus 50-ish dB down, which I think is pretty healthy.
Well, you know, I have two thoughts here. You're right, 40 dB down. Yeah, that seems okay. But by the same token, if you expect to see nothing and you see something that's at that level, you know, like at minus 50 dB, and you're thinking that's a lot when you expect to see nothing.
Yeah, but I think all the radios we've made, and I bet you, I'll pick on Frank for a second. Even Frank with his careful building, I bet you if we were to put an SA on Frank's builds, you would see stuff way down, you know, 40, 50 dB down. And and it works. Like I think you just worried over nothing, right?
Frank, I'll chip in on the shipping cost to ship one of your rigs over to Dave.
Okay.
But you know what? It would be an interesting little venture there to do make a measurement of that time.
That would be a really interesting exercise.
It would be. You're just saying that to goat me into doing this.
So I think what we need to do then is we got to get Frank to come out to one of these, you know, 1 week at Eric's cottage or 1 weekend at Eric's farm.
Yeah, you know what I thought of doing. Yeah, that's given. We have to get Frank out there for sure. Or we could do one day at Frank's. We could all go and visit. No, but you know what? Ken? That CR you've got, you know, put a spectrum analyzer on the out port and see what RF you see coming out of that port. And I know you've got a 0.1 or a 10 nano or 1 nano capacitor on the output of the SA612 that's going to, you know, short any RF coming out of that because it's supposed to be audio coming out, right? So, but it'd be interesting to put a SA on that port, on the output port, remove that and just see what RF you've got bleeding through. Because I bet you it's going to be RF bleeding through.
You mean you hope there's RF bleeding through? Because if Frank has zero.
I was talking about Ken's DCR. The DCR receiver, because that's got a SA612. It's got an audio port coming out, right?
Yeah.
Speaking of that, Ken, where with that DCR?
What's that?
Where are we at with the DCR? Because I did the board up for you, right? But I think the only thing I needed was to know what the footprints for the BNC and the pots were.
Yeah, I've got to get those. I'll try and do something this weekend.
Because I could get those boards made again. It's like $4, man, to go and we could get 5 boards made. And instead of going and milling them and doing, we just send it away 2 weeks later. We'll get boards coming $5 or $7 Canadian, including shipping. You know, like you can't beat that.
Yeah, I know. No, I just got to find the time to do stuff. There's too much going on here right now. But I'll try and get on it this weekend.
I have a question for you. Does anybody here have a tiny SA? Especially if you have a spectrum analyzer as well.
Yes, I do. Michael, I do. Yeah, I think I've turned it on once. I haven't used it. I know I should be able to use it with the nano VNA and whatnot. I just haven't had the inclination to do it. Been too busy fiddling around with other stuff, or not, as the case might be.
The reason why I ask is because one of the local hams here, he's actually taken on that new transceiver build, the T41 one that came from, what's his name? I forget.
Jack.
Jack.
Roden.
Yeah, Jack and Peter. So he's taken that on, bought the book and stuff like that. Anyway, he asked me the other day, he was over here we were having a chat, and he was saying, how well the tiny SA work? Because obviously it's a lot cheaper to buy the tiny SA than to go out and buy one of these guys, right? Especially with what Frank was saying, what 40% exchange rate now. So just wondering how. I guess Michael. I guess the question is. Well, I guess I know the answer because you said you haven't turned it on very much. But it'd be interesting to make a comparison of your spectrum analyzer and the same measurement with the tiny SA and see what the differences are.
I had thought of doing that. I just haven't got around to it. It's something I want to try.
Mm-hmm. Yeah, I'm not sure what the tiny SAs are up to now. I guess they're a little over $100, but that's still a far way off of 1,400 US.
Oh yeah, that's right.
Did you, Peter? Did you see
And if you
Charlie
blow
Morris's?
a tiny SA, it's not a big deal.
Charlie Morris's what? Oh, his latest.
Video
Yeah,
about crystal filter.
yeah, I think.
But he compared the reason saying that it's not the tiny SA, but he was talking about the VN8, the nano VN8, and he was saying he was getting completely different results when he characterizes his filter with the nano VN8 versus his SA. He's got the same SA got that it's the same scope. He's got the same spectrum analyzer, and he's got the same signal generator that I've got, exactly the same. It's kind of funny, but anyway. So he was showing results, and he was showing that the nano VNA was giving them completely different results. So it would be interesting to find out if the tiny SA is similar, or it does it does bad performance, or it does fairly good performance. That'd be good to find out.
Yeah, I haven't seen that particular video of his, but I've watched his other ones. I have to go back and see it. I guess I missed that one. That's the crystal filter one?
Yeah.
Okay.
Yeah, I can't remember. It's coming back to your conversations you were saying about the crystal filter. You're building crystal filter, and I was trying to remember going, Christ, how do we do this again? And so I started Googling videos on crystal filter, and a whole bunch came up from Charlie Morris. And there's one of them where he was building crystal filter, and he goes through he does good videos showing how he designed it, and then experimentally how he measured it. And it was a good idea.
I know. I was talking to Howard yesterday. Was it yesterday? Yeah, he was over here yesterday, and I was chatting. That was one of the conversations I had with him. I said I spent hours, days, weeks going over how to match crystals properly and going through all that stuff and generated encyclopedias full of paperwork of numbers. And here I am. I can't remember any of it. Of course, I didn't write down a how-to or anything like that. So it's like you, Dave, have to start all over again, review videos, Well, I think our manual for the SNA goes over a fair bit of it as well. But anyway, I wish I could remember everything.
Yeah, but Charlie's got a really good way of characterizing filters. It's nothing. If you think about it, it's actually pretty smart. What he does, he builds a resonator. He gets a Colpitts oscillator or something like that, right? And it's built exactly. He doesn't change anything. It's built. He unplugs a crystal. He takes a crystal, plugs it in, leaves it running for a bit of time, let it warm up, right? And then he turns on his receiver, and he zero beats the frequency that he hears on his receiver from that crystal, right? And he does that, and he then uses a spectrum analyzer, and he compares it, and he's able to get his crystals within 5 hertz. And then he builds it, and you could see the little ripple in the pass band coming because of that 5 hertz variation. And it's a clever way of doing it, as opposed to going and doing it the way we're doing, the classical way of using, some kind of characterization software, right?
There are several different types of crystal filter design. One of the most ones that I see right now that a lot of people are using is they just go and match the crystals within, for a sideband crystal within 50 hertz, and then just use the same value capacitors. They don't go and recalculate different capacitor values for everything.
When you're trying,
Yeah.
sorry, go ahead, Dave.
No, I was going to say that was basically Charlie's approach, right? He used the same value capacitors across. It's a Cohen filter, so you use the same value capacitors. And there's another guy too. I ran across another video where this guy goes and he puts an SA on the crystal filter, right? He sweeps it, right? And then he changes capacitor values. He's got pots. So he goes and he starts tweaking the outer 2 pots, then the inner 2 pots, and he keeps tweaking it, and he's showing what happens to the crystal filter passband, right? And he comes up with, it says, just keep the same version capacitors, the same value capacitors throughout the entire filter. But yeah, Dwayne, I've ran across that kind of philosophy as well.
I have a question about while we're on this subject. You got when you're measuring the characterizing the crystal, you come up with a few numbers, RS, CM, L, MQ. And if you're going to decide, okay, which crystals are you going to line up, match with each other, which ones are the most important ones to consider to match closest together? Like, let's say, for example, you got your Q and the LM, and maybe even CM is all close, but the RS is way higher than, say, maybe another one that maybe its CM or LM is a little bit off. Like, which one of those values, parameters is the more important one than another one? Do you know what I mean? I mean, it probably would help if I had a good, example, but I don't off of the top of my head. But do you follow what I'm asking? Anybody?
Yeah, I know what you're talking about. I don't know. When I started doing crystal filters early, when I got back into this, I was going through that method of matching with the different parameters and that. And later on, I just started measuring within a certain number of hertz. And I really didn't see any difference between the two.
I guess what I'm saying is, let's say, for example, if you took all your parameters are pretty much bang on, but let's say the series resistance is way high, just as a cheap example, would you throw that one away and accept a crystal that maybe not quite as, that maybe the frequency's off a little bit more, but its resistance is a lot lower? You know what I mean? Just for an extreme example.
Well, I guess it all depends on how many crystals I have to play with. Like, if I need 4 and I only have 6,
oh, then you have no choice.
Then I may have to, use an odd one.
I guess what's probably the most important thing is to minimize the amount of ripple that's in it, and you choose the crystals to have that minimal ripple in there. And if you have a little bit more increased loss through the filter, well, that's what the amplifiers are for. I don't know.
To me, that suggests that the capacitance values and whatnot are more important than the resistance, because the resistance you can correct with amplifiers, like you say. So maybe the thing to worry about is sort of matching the capacitances and whatnot. I don't know.
That resistance value, that basically affects the Q of the crystal as well.
Well, that's another thing too. You know, if some of your other numbers are way off, but the Q is way high, you know, like I say, which parameter has a higher rating of value than the other versus the others? Like what? I guess the best thing is, what do you match first? The resonant frequency, or do you measure the Q first, or like you know, like the? I'm thinking that you go for the resonant frequency, get that the closest possible, and then go down the line from there. But which is more important? If your CM and LM are there, what about your Q? What if the Q is a little bit less? Anyway, I don't know.
I'm just going to match by frequency.
What I do is
One way to tell is to actually is sweep them and see what the differences are. Like I don't have enough rabbit holes.
well,
We got a really snowy lot of snowy winter this year. Can't get out of the shack then.
a couple times doing matching crystals. I just put a little attenuator, you know, use the VNA or my SNA, and you know, attenuator input and output, you know, guesstimate what the impedance of the crystal is going to be. Use that to match frequencies. Then after I got them down the closest frequencies, I just looked at the ones with the waveforms look closest to each other.
Go ahead, Dave. Oh. Oh, okay. Yeah, I'll have to take a look at that, Dave.
Oh boy, got all kinds of stuff going on here.
Yeah, I can tell he's retired.
Sorry.
Got some.
Anyways, getting back to PCBs, I've always wondered when these guys design boards, how do they know where the vias go and how many to use?
I'm not sure I follow what you mean exactly, Ken, but
Huh?
I'm not sure I follow exactly what you mean. Like how many vias do you use?
Well, you know, like look at some of the boards that Kelly's made for our projects, and is there any logic as to where to place them and how many to have? You know, like can't you just say, for example, have one through hole come up from the ground plane if there's a ground plane on top as well?
Oh, I see what you mean. Like if you want to bond the two ground planes together, how many vias do you use? Is that what you're referring to?
Yeah.
Oh. Well, if it's anything like my LBS project, I would say that's ground loop city.
Yeah, if you've got, like I know with the MAR devices, you got to make that you got the top ground plane, bottom ground plane has got to be stitched together right around the device to make sure that some of the potentials are the same, because it's got to flow to the bottom layer or something like that. I remember if you look at the MAR 6, those mimic LNAs, they had a requirement that you have so many stitches of vias between the top layer and the bottom layer.
Yeah.
So that was the only place I ran across like stitching. But in terms of like running traces and putting vias, I try and avoid using vias as much as possible. Like with the board I did for the power amp, I've got vias. I've got vias here, but I purposely did the the trace from the power amp from the last stage. The trace here, here's where the IRF 510 sits. So the trace that goes from there to the filter here, the low pass filter, I made sure that trace is completely isolated, not close to anything, because that's running power. And so I didn't want that trace to be radiated. So I ran a via, and you can see the trace here at the bottom. That's the trace there at the bottom running power to the filter. Then I've got a via here taking it up, and it goes to an SA capacitor that goes to the filter. But if you look at that trace, there's no other traces around. I wanted to isolate that. So like there's a use where I use a via. But I wing it.
Yeah.
Who knows? Who knows if that's good or bad? I'll find out when I build it.
There's a program you can download. There's the Saturn PCB design toolkit. It's a free download. It has all kinds of calculators for width. It has things for via properties and all kinds of stuff like that. The Saturn PCB toolkit, I think it's called.
So there is some kind of science behind the vias.
It's just black magic.
Yeah.
That black magic never reveals itself when I let the smoke out of a component, though.
In your case, it's called black smoke. Alrighty. So anything else? Anybody have anything else you want to talk about or ask questions? Not. Well, should we
I'm going
wrap
to
up?
share my screen for a second.
Yeah, go ahead.
There, can you guys see this? You guys can see this, right?
Well, we can see all of us on your screen.
Can you see the screen?
Yeah.
Right. That's fine. You're seeing the screen.
What do you want to show?
Here's the.
Oh, right.
I'm going to show you in a second. This is the calculator that comes part of KiCad. So it's got RF attenuators, resistor values. It's got lines, strip lines, how to design strip lines, twisted pair, via sizes, track widths. This is what I use to measure the current. You put the current, rise in temperature, all that stuff, electrical spaces, board classes. It's got a whole bunch of calculators here. So Dwayne, I don't know if this is similar to that Saturn PCB toolkit, but this comes as part of KiCad. It's part of the calculator tools here.
Yeah, stuff looks pretty similar. I don't use KiCad, and I use this thing with the Saturn program with the design software I use.
Alrighty. Well, shall we wrap this up? What time is it? Yeah, it's almost 9 o'clock. Well, shall we call it a night, gentlemen?
Sure.
Alrighty. Well, everybody have a good night, and we'll see you on the meeting up there.
Yeah, November.
Michael.
November.
Hi, everybody.
Night.
Cheers, guys.
Michael.
73 all. Good night.
Night, guys.
Recording has stopped.
You did recordings as well, Dave?